going to look at a Bernoulli's equation problem, fluid flow problem, and this problem reads, a water pipe having a 2.5 centimeter inside radius carries water into the basement of a house at a speed of 0.9 meters per second and a pressure of 170 kilopascals. If the pipe tapers to 1.2 centimeter radius and rises to the second floor, which is 7.6 meters high, what is the water pressure at the second floor? So if any of you are in the process or recently purchased a home, it's always important to check the water pressure on the second floor. So let's look at this. What is the water pressure on the second floor? All right, so this is a case of dynamics and fluids, so we can utilize the idea of Bernoulli's equation. Let's just remind ourselves what that is. That tells us that the pressure plus 1/2 the density times the speed at 1 point squared, plus the density times g and the height at that point. It has to be conserved. This energy has to be conserved. So we have the pressure at 0.2 plus 1/2 the speed at 0.2 squared, or at 2 squared, plus that relationship to the height. All right, so we're given the pressure at 1. We're given the speed at 1. What about the height at 1? Well, anytime we're dealing with position, we always have to set a reference. So let's set our reference height, y equal to 0, where it enters the house. Then we know that at 0.2, we're at 7.6 meters. And this term goes to 0 because we're at our reference height. We're interested in the pressure at 2. We're not given the speed at 0.2, but we are given its height. So we're going to need the speed at 0.2 in order for us to solve this problem. So how do we do that? Well, we utilize the continuity relationship when dealing with fluid flow. So remember, the continuity equation told us that the area times the speed, so the bulk flow, has to remain the same, the area at a second point times the speed at that second point. So we are interested in the speed at that second point, so we have the ratio of the areas times the speed at that first point is going to give us the speed at that second point. So we know our area is pi r1 squared over pi r2 squared times the speed at 1. Our pi's are going to go away. And we have 2.5 squared over 1.2 squared times 0.9. So that gives us 3.9 meters per second for our speed coming out at the second floor. All right, now we can utilize that and our Bernoulli's principle to solve this problem. So we have 170 times 10 to the third plus 1/2 rho. We're dealing with water, so that's 1,000 times our initial speed of 0.9 squared. That term has gone away, plus our pressure at 2, which is what we're interested in, plus 1/2 1,000 times our speed of 3.9 squared, plus 1,000 times 9.8 times 7.6. All right, so let's put our terms in here. We have 170 times 10 to the third plus 0.5 times 1,000 times 0.9 squared gives us 405. That equals the pressure at 2.5 times 1,000 times 3.9 squared plus 7605 plus 1,000 times 9.8 times 7.6. 74480. So now we're going to solve for P2. So 170 times 10 to the third plus 405 minus 7605, not 76.5, 7605 minus 74480. I must have done something wrong because that is not the correct answer. So we get pressure at 2 is equal to 8.8 times 10 to the 4th pascals. So there we go. All right. So utilizing this idea of Bernoulli's principle, recognizing that we have to have this continuity relationship. Okay, so to get the speed at point 2, we have to remember the continuity equation and that bulk flow idea, and then recognizing where our parameters are and utilizing Bernoulli's to solve the problem. Good job.